Right now, underneath one of the most densely populated coastlines in Europe, the ground is rising, cracking, and shaking in a pattern scientists have not recorded in more than 40 years. On the evening of July the 31st, 2026, at 7:46 p.m. local time, a magnitude from 4. 7 earthquake tore through the Campi Flegrei caldera just west of Naples, Italy. It was shallow, only about 3 kilometers deep, and it hit hard enough to send boulders crashing down a hillside in the Girolomini area, crushing parked cars under a cloud of white dust. Power went out across entire neighborhoods. The Cumana and Circumflegrei rail lines shut down so engineers could inspect the tracks. The port of Pozzuoli closed completely after deep cracks appeared in the access lanes to the commercial docks, cutting off ferry service to the islands of Przaida and Ischia in the middle of peak summer tourist season. Somewhere between 21 and 26 people were injured, 2 seriously. Thousands of residents spent the night outside, too afraid of aftershocks to go back indoors. And Italian officials confirmed almost immediately that this was the strongest earthquake to hit the region in 4 decades. Not the strongest this year, not the strongest since the unrest began, the strongest in 40 years. Today we are going to break down exactly what is happening beneath Naples, why scientists have been watching this specific patch of ground with genuine unease for the past 2 decades, what a newly identified mechanical threshold means for the years ahead, and whether the word most people jump to the moment they hear supervolcano actually applies here. No exaggeration, no doomsday spin, just the geology, the data, and what it actually means for the roughly 3 million people living in its shadow. Before we go further, if earthquake and volcano stories like this one matter to you, go ahead and subscribe now so you do not miss the next update, because this situation is genuinely moving fast. And drop a comment telling me if you have ever felt a volcanic tremor yourself, or if you would ever consider living somewhere like this. I read every single one, and I want to know where you are watching from. So let's actually understand where we are talking about, because Campi Flegrei is not a mountain. That is the detail that catches most people off guard. When you hear volcano, you picture a cone, a peak, something you could point to on a horizon the way you'd point to Vesuvius, which sits just 18 kilometers away and is famous for burying Pompeii in the year 79. Campi Flegrei is the opposite of that. It is a depression. A 12 by 15 kilometer sunken basin, pockmarked with at least 24 craters, cones, and vents, stretching from the western suburbs of Naples through the town of Pozzuoli and out toward Pozzuoli. The ancient Greeks and Romans did not just find this place unsettling, they built mythology around it. The name Phlegraian Fields comes from the Greek word phlegra, meaning to burn. The Romans placed the literal entrance to the underworld at Lake Avernus, one of the caldera's crater lakes, because sulfur fumes rose from the ground and birds reportedly dropped dead flying over it. This was not superstition pulled from nowhere. People living there for thousands of years watched the earth breathe, watched steam curl out of cracks in the rock, and concluded, reasonably enough for the time, that they were standing on top of something otherworldly. What they were actually standing on top of is a caldera formed by 2 of the most catastrophic volcanic events in European prehistory. The first happened around 250 years ago, an eruption so massive it is now linked by some researchers to major climate disruption across the continent, dropping ash as far as Russia and possibly contributing to environmental stress that some scientists connect to the decline of Neanderthal populations in Europe, although that particular link remains debated among researchers. The second caldera-forming eruption came around 15,000 years ago. Both events were large enough to fundamentally reshape the landscape and leave behind the wide, low basin that 500,000 people now call home. Since those prehistoric eruptions, Campi Flegrei has erupted dozens of times at smaller scales, with the most recent eruption happening in 1538, when the ground near Pozzuoli rose so violently over the course of about a week that it formed an entirely new hill called Monte Nuovo, essentially manufacturing a small mountain out of nothing in a matter of days. That eruption displaced the town's population and permanently reshaped the coastline. It is the reference point Italian volcanologists keep coming back to, because it is proof that this system does not just simmer. It has, within recorded history, actually gone. Now here is where the story gets specific to right now, to this year, to the reason this earthquake in July was different from all the smaller tremors that have rattled the region for the past 2 decades. Campi Flegrei has been in a documented state of unrest since 2005, and the driving force behind that unrest is something called bradyseism, a slow, cyclical rising and sinking of the ground caused by pressure changes deep underground. Since this current phase began, the ground near Pozzuoli has risen by more than 140 centimeters, close to 4.5 feet of vertical uplift over 20 years. Picture the floor of an entire town slowly jacking itself upward, inch by inch, year after year, while the buildings, roads, and sewer systems on top of it are forced to absorb that movement. The uplift has not been smooth or constant. It has accelerated. And accelerating right alongside it has been the seismicity, meaning the number and intensity of small earthquakes generated as the crust struggles to accommodate the rising pressure underneath it. To understand why an earthquake happens at all in a place with no visible fault line the way California has, you need to understand what is physically happening a few kilometers beneath Pozzuoli's streets. Roughly 3 kilometers down, there is something scientists call the brittle ductile transition zone. Above that depth, the rock behaves in a brittle way, meaning it can crack, snap, and shift suddenly the way a dry stick breaks. Below that depth, heat and pressure are high enough that rock behaves more like a ductile material, bending and flowing gradually instead of snapping. Underneath that transition zone at Campi Flegrei sits a reservoir of magmatic fluid, a mix of magma and magmatic gases, slowly building pressure. For years, the crust above that pressure zone responded elastically, meaning it stretched and absorbed the strain the way a rubber sheet stretches under a push, then largely returned to shape when the pressure eased. That was the pattern for most of the unrest between 2005 and roughly 2020. But in a 2023 study, volcanologist Christopher Kilburn and his colleagues identified something different happening in the data. Since around 2020, the relationship between how much the ground was rising and how many earthquakes that uplift was producing had shifted. The crust was no longer just stretching elastically. It had entered what researchers call an inelastic regime, meaning actual permanent rock failure, real fracturing, was starting to outweigh simple elastic flexing. In plain terms, the ground was not just bending anymore, it was starting to break. That distinction matters enormously because it is the difference between a system storing stress safely and a system that is running out of room to store it. Think of it like a bag of rice sitting on a wooden shelf. In the elastic phase, the shelf bows slightly under the weight, but it flexes back close to flat every time you take a little weight off. That is healthy, reversible strain. In the inelastic phase, the wood fibers themselves start splintering under the load. The shelf no longer fully springs back. Each additional bag you add is not just testing the shelf's flexibility anymore, it is testing how much actual structural damage the wood can accumulate before it simply gives way. Nobody watching that shelf from across the room would necessarily notice the difference between phase 1 and phase 2 just by eyeballing it. You would need instruments measuring the exact flex, the exact creak, the exact rate of change to know which phase you were actually in. That is precisely the role INGV's monitoring network plays underneath Naples, and it is exactly why the 2020 shift Kilburn's team identified went largely unnoticed by the general public, even though, in hindsight, it may turn out to be the single most consequential data point of this entire 20-year unrest episode. Follow-up research published through Communications. Earth and Environment went further, identifying the birth of what researchers describe as a new volcanotectonic fault forming inside the caldera, with earthquake locations clustering along a specific plane, consistent with an extensional fault actively growing in response to the pressure below. And using what is called a failure forecast method, a mathematical framework that models how systems accelerate toward a critical mechanical threshold, researchers led by Andrea Bevilacqua calculated a probability curve for when Campi Flegrei's crust might reach that threshold. Their modeling placed a 50% probability of reaching a critical state around 2023, and a 95% probability by 2031. Other analyses building on this framework have pushed the upper end of that window out toward 2033. I want to be very precise about what that threshold actually means, because this is the single most misunderstood part of the entire story. And it is exactly the kind of detail that gets flattened into clickbait the moment it leaves the scientific literature. Reaching a critical mechanical threshold does not mean an eruption is scheduled. It means the crust reaches a point where it can no longer safely absorb rising pressure through gradual small-scale fracturing, the way it mostly has for the past 2 decades. Past that point, the same amount of added pressure produces disproportionately larger, more sudden episodes of rock failure. Bigger earthquakes become mechanically easier to produce because the rock has less elastic give left in it. It is the geological equivalent of bending a paperclip back and forth. The first dozen bends barely change anything, but each bend work hardens the metal a little more, and at some point, one more ordinary-looking bend is the one that snaps it. Nobody can tell you in advance which bend that will be. What the data can tell you is that you are getting closer to it. That is exactly the backdrop against which this year's earthquakes need to be read. February 2026 saw a sharp seismic swarm with the Italian National Institute of Geophysics and Volcanology, known as INGV, recording 70 earthquakes in a single week between February 23rd and March 1st. On May 21st, 2026, a magnitude 4. 4 earthquakes struck offshore between the Pozzuoli and Boccoli sectors of the caldera at a depth of about 3 kilometers, kicking off a swarm of 12 total earthquakes before it wound down. And then came July the 31st. A magnitude 4. 7. The the strongest instrumentally recorded earthquake since continuous monitoring of this current unrest phase began, surpassing 2 magnitude 4. 6 events recorded the previous year that had themselves been described as the strongest in 40 years at the time. Do you see the pattern forming there? Each new record earthquake displaces the last record earthquake within a matter of months, not decades. INGV confirmed that July 31st epicenter sat near the Solfatara crater in Pozzuoli, the exact spot where sulfurous steam still visibly vents from the ground today and has, for centuries, at a depth of roughly 3 kilometers, right around that brittle ductile transition zone we just talked about. At least 10 aftershocks followed within hours, the largest a magnitude 3. 8 striking the Gulf of Pozzuoli around 10 p.m. that same night. Deputy Prime Minister Antonio Tajani addressed the public directly afterward, saying the government was committed to providing full assistance to displaced residents and to finding a lasting solution for buildings that had been declared unfit for continued use. That is not rhetoric you hear after minor tremor. That is the language of officials who understand this is now a recurring, escalating situation rather than an isolated event. Now, if you are wondering whether Naples has actually seen anything like this before, the answer is yes, and the precedent is genuinely important context. Between 1982 and 1984, Campi Flegrei went through what Italians still refer to as il bradisismo, a 2-year seismic crisis during which the ground beneath Pozzuoli rose by nearly 2 meters, and the town recorded literally tens of thousands of earthquakes. The largest events reached around magnitude 4, and the shaking became so relentless and buildings became so structurally compromised that authorities evacuated roughly 40,000 people from the historic center of Pozzuoli, essentially emptying out the heart of the town. Many of those buildings were never reoccupied. That crisis eventually subsided without an eruption, and the ground actually began slowly sinking back down afterward, a partial deflation that gave residents and scientists alike a sense that the danger had passed. It had not passed. It had paused. The current unrest phase that began in 2005 has now not only caught up to the uplift levels seen during that 1980s crisis, it has exceeded them. And unlike the 1980s episode, this current phase has continued accelerating rather than reversing. Longtime residents in Pozzuoli today describe living with the ground as a kind of uneasy generational familiarity. Local reporting has captured residents saying they can get scared sometimes, but rarely feel truly terrified because the volcano has simply always been part of daily life there. That kind of resigned coexistence is understandable after multiple generations of false alarms. But normalization is also precisely the psychological trap that geologists worry about most, because the data underneath that lived experience has genuinely changed character since 2020 in a way that casual observation on the street cannot detect. So let's actually address the question everybody wants answered the moment they hear the word supervolcano, because this is where a lot of online commentary gets the danger completely backwards. The same way it does every single time Yellowstone so much as hiccups. Is Campi Flegrei building toward another Pompeii scale, ash blotting out the sun catastrophe? Based on everything currently measured by INGV, the honest answer is no, not right now, and not in the way that scenario typically gets imagined. The volcanic alert level for Campi Flegrei currently sits at yellow, meaning attention, not the red level that would indicate an eruption is imminent or underway. There is no confirmed evidence of fresh magma actively rising toward the surface. The geochemical monitoring, which tracks the composition and temperature of gases escaping through vents like Solfatara, does show long-term heating trends and increased fluid emission in the hydrothermal system. But scientists studying this data have increasingly converged on an important distinction. What appears to be driving the majority of the current unrest is not necessarily magma itself pushing upward, but rather pressurized magmatic gases, primarily carbon dioxide, building up beneath that sealed, brittle ductile boundary and physically deforming the rock above it, the same fundamental pressure cooker mechanism you see behind smaller hydrothermal explosions, places like Yellowstone, just operating at a vastly larger regional scale here. A 2023 study published in the journal Geology and a follow-up 2025 study in Science Advances both focused specifically on this carbon dioxide behavior, and the researchers behind them describe something almost counterintuitive. If a significant portion of Campi Flegrei's unrest is being driven by gas pressure rather than magma migration, then, in theory, that gas pressure is something engineers could eventually learn to manage through controlled release systems or strategic monitoring of specific vent pathways, rather than something that is entirely unstoppable once set in motion. That does not mean anyone is drilling relief valves into a supervolcano tomorrow. It means the scientific picture is more nuanced, and in a strange way more hopeful than the pure doomsday framing suggests. The system's most immediate threat may not be an unstoppable magmatic surge. It may be a pressure system that, with enough research and monitoring infrastructure, we could eventually learn to work with. But here's the part where I need to be just as clear about what the data is not saying. Because reassurance about a caldera-scale super-eruption does not mean there's no real hazard here at all. There absolutely is, and it is the same category of hazard we have talked about before when it comes to places like Yellowstone, just wearing a different, arguably more dangerous costume. Because at Campi Flegrei, that hazard sits directly underneath a modern European city rather than a remote national park. The real, immediate danger is strong, shallow earthquakes, exactly like the one on July 31st, capable of collapsing older, structurally vulnerable buildings, triggering landslides on the region's soft volcanic hillsides, damaging critical infrastructure like ports, rail lines, and water systems, and doing all of that with essentially no meaningful advance warning beyond the seconds a seismic sensor can provide once rupture has already begun. Pozzuoli and the surrounding towns are built largely on volcanic tuff, a rock that is relatively easy to carve and build with historically, which is exactly why ancient builders favored it, but which also fractures and crumbles differently than harder bedrock under strong shaking, a factor engineers believe directly contributed to the hillside collapse and building damage seen after the July earthquake. Layer on top of that a second, entirely separate hazard category tied to the caldera's volcanic gas system. Solfatara and other vents in the area continuously release carbon dioxide, hydrogen sulfide, and other gases, and in low-lying or enclosed areas, these gases can accumulate to dangerous concentrations, a hazard that has already caused fatalities in the region, in past decades unrelated to any major eruption at all. So when you strip away the Supervolcano headline and look at what has actually been injuring and displacing people in 2026, it has been earthquake shaking and its direct physical consequences. Not lava, not pyroclastic flow, not an ash column blotting out the Mediterranean sun. Understanding that distinction is not about minimizing the danger. It is about aiming your concern at the thing that is statistically, right now, actually the threat, rather than the thing that makes for a better disaster movie trailer. It is also worth understanding just how much better equipped scientists are to actually see this unfolding compared to even a decade ago, because the instrumentation gap matters as much here as the geology itself. INGV's Osservatorio Vesuviano, the observatory responsible for monitoring both Vesuvius and Campi Flegrei, runs a dense network of seismometers, GPS stations, and gas sampling equipment across the caldera, feeding continuous real-time data back to Naples around the clock. Satellite radar interferometry, a technique that can detect ground movement of just a few millimeters from orbit, now lets researchers map the entire uplift pattern across the caldera in a single image rather than relying purely on scattered ground stations. The combination is exactly how scientists were able to identify the new volcanotectonic fault we mentioned earlier, by watching earthquake epicenters slowly organize themselves along a single consistent plane over a period of years, a pattern that would have been essentially invisible with the sparser instrumentation available during the 1980s crisis. This matters because it means the picture emerging from Campi Flegrei today is not guesswork dressed up as science. It is the product of genuinely dense, high-resolution monitoring, catching subtle structural changes that would have gone completely undetected a generation ago, which is exactly why researchers are willing to put specific years like 2031 or 2033 into published, peer-reviewed probability models, instead of vague, hedged language about the coming decades. Let's talk about scale for a second, because comparing Campi Flegrei to something like Yellowstone actually helps put both places in proper perspective, and the comparison cuts in a genuinely surprising direction. By raw eruptive volume, Yellowstone's largest prehistoric eruptions were considerably bigger than either of Campi Flegrei's two caldera-forming events. Yellowstone sits largely within a national park, with a relatively small resident population directly inside its caldera boundary and a robust, decades-old dedicated volcano observatory monitoring it around the clock. Campi Flegrei, by contrast, has roughly 500,000 people living directly inside its caldera right now, today, going about ordinary life, buying groceries, sending kids to school, running businesses, on top of the exact ground that has produced two civilization-altering eruptions in the last 40,000 years. Zoom the lens out further, and the greater Naples metropolitan area, home to more than 3 million people, sits well within potential range of pyroclastic flows and heavy ashfall in any large-scale eruption scenario, which is precisely why, by population exposure rather than raw geological power, researchers increasingly describe Campi Flegrei as the single most dangerous supervolcano caldera on the entire planet. It is not the biggest gun in the world's geological arsenal. It is simply pointed at more people than any other one is. There is a version of this story that focuses purely on the frightening end of things, and I want to resist that, because the last several years of research on Campi Flegrei have also produced genuinely constructive ideas about risk reduction, not just warnings. Researchers behind the carbon dioxide studies we mentioned have specifically floated the concept of monitored, engineered degassing at controlled points around the caldera, essentially giving pressurized gas an intentional, closely watched pathway to escape, gradually, rather than letting it build indefinitely beneath a sealed cap of rock. This is not a new idea invented for headlines. Engineers already manage analogous pressure systems in geothermal energy fields around the world, extracting heat and gas from deep reservoirs under carefully controlled conditions. Applying that kind of thinking to a live volcanic caldera sitting under a major city is an entirely different scale of challenge, and researchers themselves describe it as requiring careful design, extensive community input, and constant long-term monitoring rather than something that could be implemented quickly. But the mere fact that credible volcanologists are seriously discussing intervention, rather than treating Campi Flegrei purely as an unstoppable countdown, tells you something important about where the scientific consensus actually sits. This is being treated as a manageable, monitorable hazard requiring serious investment, not as an inevitable catastrophe with no meaningful human agency involved. Understanding the actual numbers behind these earthquakes also helps put the recent activity in honest context, because a magnitude 4, 7 sounds almost unremarkable if you're used to hearing about magnitude 7 and 8 disasters elsewhere on the planet. But remember that the moment magnitude scale is logarithmic, not linear, meaning each whole number increase represents roughly 31 times more energy release, not simply one more on some evenly spaced ruler. A magnitude 4, 7 sits well below the threshold of a truly catastrophic tectonic earthquake, which is exactly why the fire service reported no major structural collapses among occupied buildings and no emergency rescue operations. But a shallow magnitude 4, 7 hitting directly beneath a dense urban area built substantially on older toughened masonry construction is an entirely different physical experience than the same magnitude occurring far offshore or deep underground, somewhere remote, which is exactly the same depth and location lesson we've seen play out in earthquake coverage from other regions this year. Depth and proximity to population turn a moderate number into a genuinely frightening night for hundreds of thousands of real people, even when the geological textbook definition of the magnitude sounds modest on paper. So where does all of this actually leave things going forward, and what should you actually be watching for if you want to follow this story honestly, rather than through whatever version shows up in your social media feed next? First, keep an eye on the frequency and magnitude trend of the earthquake swarms themselves. INGV publishes weekly seismic bulletins for Campi Flegrei, and the pattern researchers are watching for is not necessarily one single dramatic event, but a continued climb in both the number of earthquakes per week and the proportion of those earthquakes crossing into the magnitude 4 range, because that pattern is exactly what Kilburn's inelastic failure model predicts as the crust approaches its mechanical limits. Second, watch the uplift rate itself, currently measured at roughly 10 millimeters per month according to the most recent bulletins, because a sudden acceleration or deceleration in that number would signal a meaningful change in the pressure dynamics below. Third, and this is the one actual scientists themselves say matters most for near-term public safety rather than long-term forecasting, watch how Italian civil protection authorities continue adjusting their evacuation planning. Italy already maintains a formal emergency plan for Campi Flegrei's designated red zone, the area considered at highest risk in a genuine eruption scenario, covering a population of roughly 500,000 people across multiple municipalities, with a target evacuation window built around ferries, expanded road capacity, and coordinated rail movement designed to move that population out within on the order of 3 days once red alert conditions were ever actually declared. That plan gets tested, refined, and publicly discussed more seriously every time a swarm like February's or an earthquake like July's makes headlines, and the seriousness with which officials are treating post-earthquake building inspections and displaced resident support this year is itself a meaningful signal about how this is being taken at the institutional level, separate from what any single seismic reading shows. If you actually live in or are visiting the Naples and Pozzuoli area, the practical guidance mirrors what we would tell anyone in any seismically active region, adjusted for the specific gas and landslide risks unique to a caldera environment. Know your building's structural history if you can, because older, unreinforced masonry and tough construction is disproportionately vulnerable to the kind of shallow, sharp shaking this region produces. Know your evacuation routes inland and away from hillsides, because the loose volcanic soil in places like the Girolomini area has already demonstrated it can fail during moderate shaking, independent of any eruption whatsoever. Keep basic emergency supplies on hand, water, a flashlight, any needed medications, the same fundamentals that matter in any earthquake zone anywhere on Earth. and take official INGV and Italian civil protection alerts seriously, rather than relying purely on how the ground feels underfoot in the moment. Because the entire point of instrumented monitoring is that it can detect trends the human body simply cannot. It also helps to know how this compares to other restless calderas scientists watch closely around the world, because Campi Flegrei is not operating in total isolation as a case study. Long Valley caldera in California, Taupo in New Zealand, and Yellowstone in the United States all show broadly similar cycles of uplift, subsidence, and swarm-driven seismicity tied to fluid and gas movement in the crust above their respective magma systems. What sets Campi Flegrei apart within that group is not the intensity of its unrest, which is actually fairly moderate compared to some historical uplift episodes recorded at Long Valley, but the sheer density of vulnerable population sitting directly on top of it, combined with a documented eruption within the last 500 years, proving the system is neither dormant nor purely theoretical. That combination of recency, activity, and population exposure is precisely why Campi Flegrei consistently appears near the top of global volcanic risk indices compiled by organizations like the Smithsonian Institution's Global Volcanism Program, even when its raw geological potential is not the largest on the planet. Risk, in other words, is never just about how big the system could get. It is about how big the system could get multiplied by how many lives sit directly in its path. And by that measure, very few places on Earth carry the same weight as the ground beneath Pozzuoli. Stepping back from Naples specifically, the broader lesson Campi Flegrei offers the rest of the world is one worth sitting with for a moment because it echoes something true about every major geological hazard we've covered. The danger a volcanic or seismic system poses is never just a function of its raw geological power. It is that power multiplied by how many people live inside its reach, and how seriously those people and their governments prepare for the version of the disaster that is actually most probable, rather than the version that makes for the most dramatic headline. Campi Flegrei is not a ticking countdown to a sky-darkening super eruption next week or next year. What it is, according to essentially every piece of published research on the subject, is a genuinely stressed section of the Earth's crust that has measurably crossed from elastic, self-correcting behavior into a phase of accumulating permanent fracture, sitting directly beneath one of the most historically significant and densely populated coastlines on the planet, with a scientifically modeled window of heightened risk that current research places somewhere in the next several years rather than the next several decades. That is not a reason for panic. It is exactly the kind of information that should quietly shape infrastructure investment, building codes, and emergency planning long before any single dramatic event forces the issue. The same lesson that separates places which survive major seismic events with minimal loss of life from places that do not. We are going to keep tracking every new INGV bulletin, every notable swarm, and every update to Italy's evacuation planning as this situation continues developing. Because this is exactly the kind of slow-building story that suddenly matters enormously the moment it stops being slow. If you want to stay current on it, subscribing is genuinely the easiest way to make sure you see the next update the moment there is real news, rather than stumbling across it days later buried in your feed. And I would love to actually hear from you on this one. Do you think authorities in Naples are moving fast enough on evacuation planning, given what the last 2 decades of data now show? Or do you think there's still time to watch and wait? Let me know down in the comments, and if this kind of deep, evidence-based breakdown is something you want more of. A like on this video genuinely helps more people see it, and sharing it with someone who might find this useful costs you nothing but takes this information a little further. The ground beneath Naples has been rising for 21 years now. Whatever comes next, we will be here to break it down the moment the data changes. See you in the next one.